You know that specific feeling of dread when you're trying to run a massive new video game or
Oh, yeah. Or a heavy 3D render.
Right, exactly. A heavy render on your computer and everything just freezes. The fans spin up like jet engines and then
Crash the desktop.
yeah, crash the desktop out of memory.
The dreaded OM error. I mean, it is the absolute bane of every PC gamer and video editor out there.
It really is. Now, I want you to imagine that frustration, but instead of trying to play cyberpunk, you are trying to build a digital brain.
Right.
A brain capable of actually understanding human language. And instead of a gaming PC, you have a warehouse full of the most expensive computing hardware on Earth, and it is still crashing.
Yeah, that is the reality of modern AI.
Yeah.
We talk about intelligence and reasoning a lot, but
underneath it all, there's a limit.
exactly. Underneath the poetry and the code, there is a hard physical limit. It's really a logistics problem.
And that is our mission for this deep dive. We are looking at the exact moment the brain got too big for the jar. We're pulling apart a foundational paper from NVIDIA called Megatron-LM.
Right, so the full title is Megatron-LM, Training Multi-Billion Parameter Language Models Using Model Parallelism. It was published by Shuibi and the team at NVIDIA back in late 2019.
It's a dense paper, I'm not going to lie. But it is essentially a detective story.
It really is.
It's about hitting a wall, a hard memory wall, and finding a really surgical way to break through it.
Yeah.
So if you're a listener who knows your GPTs from your BERTs, but you've never really looked under the hood at the plumbing that makes them possible, this one is for you.
We're going to look at how you take a mathematical model that is physically larger than any single computer chip in existence and somehow, slice it up so it can run across hundreds of chips simultaneously.
Without breaking.
Exactly, without breaking.
So let's set the scene. We're in the era of the transformer explosion. Natural language processing, or NLP, has moved on from simple tricks. We are now pre-training massive models.
Right. We saw the rise of BERT and GPT-2. And the research community realized something very quickly, which is that size matters.
Yeah.
It wasn't just a hunch. It was an empirical fact. If you make the model bigger, like more parameters, more layers, and feed it more data, it just gets smarter.
It's almost a law of physics at this point. Bigger model equals better accuracy.
Exactly. It's what we call monotonic improvement. It doesn't zigzag or plateau early. It just goes up. But this created a crisis.
Because a model is just a collection of weights.
Yes. Just numbers stored in memory.
Yeah.
So as you chase that intelligence, the file size of the model completely explodes.
And that's where we hit the hardware reality. The paper references the NVIDIA V100 GPU. At the time, this was the absolute beast of the industry.
Oh, yeah.
It had 32 gigabytes of high bandwidth memory.
Which sounds like a lot if you're comparing it to, say, a phone. But a billion parameter model isn't just storing the weights.
Right. It needs more than that.
It needs to store the optimizer states, the gradients, the activations. It all adds up incredibly fast.
So if I have a model that needs 60 gigabytes of space just to even turn on, and I try to load it onto a 32 gigabyte card.
It crashes. You literally cannot start the training run. It's physically impossible.
Okay, so the standard solution in the industry prior to this was something called data parallelism. Walk us through that. Why didn't that work here?
So data parallelism is the default setting. Imagine you need to read an entire library of books. That is your training data.
Okay, I'm picturing a massive library.
Right. In data parallelism, you hire 10 students. You give each student a full copy of the same brain, the same model.
So every student is essentially a clone. They all have the full set of instructions already in their heads.
Correct. And then you split the library. Student 1 reads the first shelf, student 2 reads the second shelf, and so on.
Got it.
They learn independently, and at the end of the day, they meet up, compare notes, and update their brains to match each other.
That sounds incredibly efficient. I mean, that's how most distributed computing works, right?
It is efficient, but it relies on one fatal assumption.
That the student's head is big enough.
Exactly. That the head is big enough to hold the instructions.
Yeah.
If the brain, the model, is larger than the GPU memory, you can't make the copy. You can't even fit one student in the room.
So data parallelism is entirely useless if the model itself is too big. You can't copy what you can't load.
Precisely. So if you can't copy the model, you have to split the model. And this is what we call model parallelism.
Sticking with the analogy then, instead of 10 students each having a full brain, we are taking one giant brain and spreading it across 10 students.
Right. Student A holds the memories, student B holds the grammar, student C holds the vocabulary,
Wow.
and they have to work together to act as one single intelligence.
But that sounds like a logistical nightmare, because if student A needs information that student B has, they have to stop and ask for it.
And that right there is the bottleneck. In computing, doing math on a chip is incredibly fast. Moving data between chips, even with high-speed cables, is incredibly slow by comparison.
It's the difference between thinking a thought and shouting it across a crowded room.
Exactly. So the challenge isn't just splitting the model. It's splitting it in a way that minimizes the shouting.
Right. So before Megatron-LM, how are people trying to solve this?
They tried something called pipeline parallelism. Think of it like an assembly line. Layer 1 is on GPU 1. It does its math, then passes the result to GPU 2, which has layer 2.
That seems logical enough, like a bucket brigade.
It is logical, but it creates bubbles in the timeline. If GPU 2 is working on the data, GPU 1 is just sitting there doing nothing, waiting for the next batch.
So you have really expensive hardware just idling.
Yes, it's super inefficient. Plus, implementing it required complex code and custom compilers.
And this is where NVIDIA's team stepped in. They wanted a solution that was efficient, keeping all the chips busy all the time and simple.
Right. They didn't want to rewrite the entire PyTorch library or build a brand new compiler from scratch.
So they came up with intralayer model parallelism, which means instead of cutting the model horizontally, layer by layer,
They cut it vertically through the layers.
This is the surgical part. Let's really break down the anatomy of a transformer model to understand this surgery. Because if we don't get the anatomy right, the surgery won't make sense.
Good point. So a transformer block has two main organs, if you will. There's the self-attention mechanism and there's the multi-layer perceptron, or MLP.
Let's start with the MLP. This is basically a massive block of matrix multiplication, right?
It is. It consists of two major operations. You take your input vector, multiply it by a huge matrix to expand it. That's the first GMM general matrix multiply.
Okay, expand it.
Then you apply an activation function like GLU. And finally, you multiply it by a second matrix to shrink it back down.
Okay, so expand, activate, contract, two big math problems. How do you split a math problem across two chips without them needing to talk constantly?
This is the clever bit. They used a property of linear algebra. For the first matrix, the expansion, they split it by columns.
By columns.
Yes. Imagine slicing a spreadsheet vertically. GPU 1 takes the left half, GPU 2 takes the right half.
Okay, so if I input a vector, both GPUs get the exact same input. GPU 1 multiplies it by the left half, and GPU 2 multiplies it by the right half.
Right. And they produce two different output vectors. And here's the trick. They don't sync up yet.
They don't talk at all.
Nope. They keep those partial results local. They run them through the activation function entirely independently.
So they're still working in silos, no shouting across the room yet.
No shouting. Then comes the second matrix, which is the contraction phase. For this one, they split it by rows.
Rows. Why switch from columns to rows?
Because of how matrix multiplication works. If you take the output from the first step and multiply it by the row split matrix, the math works out such that the final result is just the sum of what GPU 1 calculated and what GPU 2 calculated.
Wait, really? So the math essentially resolves itself into two separate piles that just need to be added together at the very end.
Exactly. They do all the heavy lifting independently. Only at the very finish line of that layer do they actually need to communicate.
Wow.
They perform one all-reduce operation.
Define all reduce for us.
It's a group sync. Every GPU shouts its total, the network adds them all up, and sends the final combined total back to everyone, and it happens instantly.
So instead of constant chatter throughout the calculation, it's just work, 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 quick, sync, done.
Precisely. By splitting the first matrix by columns and the second by rows, they reduce the communication to just one singular sync point per block.
That's brilliant.
It keeps the GPUs compute bound, meaning they are limited only by how fast they can do the math, not how fast they can talk to each other.
Okay, so that's the MLP sorted. But the soul of the transformer is the attention mechanism. That's the part that figures out context. Is that harder to split?
Surprisingly, no. It's actually easier. Transformers use multi-head attention. Think of a hydra with many heads.
I like the Hydra analogy.
Each head in the attention layer looks at the sentence independently. So one head might be looking for grammar relationships, another might be looking for, which he refers to John.
So they are already separate operations by design.
Exactly. So if the architecture already has 12 separate heads,
You just give 6 to GPU A and 6 to GPU B.
you got it. It's inherently parallel. They split the key, query, and value matrices, which are the components of attention by columns. Just like the MLP, they work independently and only sync up once at the end.
It really feels like they are using the model's own design against it. Or rather, for it.
They are. They aren't forcing a square peg into a round hole here. They looked at the math and found the natural fault lines where the rock splits easily.
So they have this theory. They wrote the code in standard PyTorch, keeping it simple. Now they actually have to test it, and they start with GPT-2.
Right. They decided to scale GPT-2 up to 8.3 billion parameters. For context, the original GPT-2 large was only 1.5 billion.
So they are quintupling the size right out of the gate.
And it worked flawlessly. The loss curves went down, the model got much smarter, it completely validated the whole approach.
But then the plot twist, they tried to apply this exact same logic to BERT.
Yeah. BERT is a different beast entirely. GPT reads left to right like a human. BERT reads bidirectionally. It sees the whole sentence at once.
Okay.
When they tried to scale BERT past roughly 2 billion parameters using this Megatron method, it broke.
Broke how? Did it just crash like the memory error?
Worse, it stopped learning. The loss, or error rate, stopped going down and actually started spiking. The model became highly unstable.
That is a nightmare scenario. You've built this massive supercomputer, designed this elegant parallel system, and the AI just refuses to learn anything.
It really challenged that monotonic improvement rule we talked about earlier. Yeah. For a minute, it looked like maybe there was a hard limit to how smart BERT could actually get.
So did they just assume BERT was flawed? Or did they think their splitting method was the problem?
They suspected the architecture itself couldn't handle the scale, so they popped the hood. And this is where we get into layer normalization, or layer norm.
Layer norm is basically the reset button that keeps the numbers from spiraling out of control between the layers, right?
Essentially, yes. In the original BERT design, which was the blueprint everyone used, layer norm was placed after the attention and MLP blocks.
So that's called post-norm.
Right, post-norm.
Okay, so you do all the math and then you normalize the result.
Exactly. But the NVIDIA researchers hypothesized that at this massive scale, the post-norm setup was causing the gradients, the learning signals, to get really messy as they flowed back through the network.
Messy how?
The signal was essentially vanishing or exploding.
Right.
The math was just getting too big too fast.
So the actual learning signal was getting lost in the noise.
Exactly. So they made a tweak. They moved the layer norm to the input of the blocks. They put the filter before the processing, not after. They called it pre-norm.
That sounds like such a minor detail. You're just moving a box on a flowchart 3 inches to the left.
In deep learning, those inches are miles. That one single change fouled everything.
Just like that.
Just like that. The instability completely vanished. They were able to train a 3.9 billion parameter BERT, and the accuracy went through the roof.
It's absolutely fascinating to me that the barrier wasn't the intelligence of the researchers or even the power of the hardware, but just the order of operations.
It really highlights that as these models get bigger, the standard ways of doing things just break down. You have to reevaluate the basics. The physics of the model change when it gets that heavy.
Let's talk about the results, because they didn't just run this on a couple of gaming cards. They went huge.
They used 32 DGX2H servers.
Which is?
That is a cluster of 512 Tesla V100 GPUs.
512 GPUs. That is an unbelievable amount of heat.
And they connected them with NVSwitch and InfiniBand. This is crucial because, remember, even with their clever slicing, the GPUs still need to do that all-reduced sync at the end of every single layer.
Right.
If the cables between the computers are slow, the whole thing stalls out anyway.
So what was the verdict? How efficient was it?
This is the number that really dropped jaws in the industry. They achieved 76% scaling efficiency.
Contextualize that for us. Why is 76% impressive? Shouldn't a perfect system be 100%?
In parallel computing, you essentially pay a tax for every new worker you add. If you have 2 people digging a ditch, you might get double the speed. But if you have 500 people digging a ditch...
They spend half their time just bumping into each other.
Exactly. Usually efficiency plummets as you scale up.
So getting 76% efficiency out of 512 separate chips
is unheard of. It means they were utilizing 3/4 of the theoretical maximum power of that massive supercomputer. They sustained 15.1 petaflops of compute.
Petaflops? That's a quadrillion operations per second.
It is a staggering amount of math. It basically proved that the communication overhead, the shouting across the room, had been minimized to the point where it barely mattered.
And the models themselves, did they actually get smarter, or was this just a big flexing of engineering muscle?
Oh, they definitely got smarter.
Yeah.
The 8.3 billion parameter GPT-2 achieved state-of-the-art results on the Wikitext 1-3 benchmark.
Okay.
Its perplexity, which is a measure of how confused the AI is, dropped to 10.8. The previous best was 15.8.
In the world of AI, a drop of 5 points is massive.
It's a huge leap, and the 3.9 billion parameter BERT absolutely crushed the race dataset.
Remind me, RACE is the reading comprehension one.
Yes, it's a reading comprehension test designed for middle and high school students. The model hit 90.9% accuracy.
That is probably higher than I would get on a high school reading test today.
Likely higher than most of us, honestly.
So they proved the engineering works. They proved the pre-norm architecture stabilizes the training for bidirectional models. But there is another concept in the paper I want to touch on because it really explains how we got to where we are today.
Orthogonality.
Yes, the concept of orthogonality, which is really just a fancy word for mix and match.
Right. We talked about data parallelism, where you copy the model, and model parallelism, where you slice the model. The paper points out that these aren't mutually exclusive.
Right. Megatron-LM allows you to actually do both at the same time.
And this is key. In their biggest experiment, they used 8-way model parallelism. So 8 GPUs team up to form one single Megatron brain.
Okay, so that handles the memory limit. The brain fits perfectly because it's split 8 ways.
Exactly. But they had 512 GPUs available. So what did they do with the rest?
They made copies.
They made 64 copies of that 8 GPU Megatron brain.
So they have 64 giant brains, each made of 8 interconnected chips, all reading different parts of the library at the exact same time.
Exactly. That is how you scale to the moon. You slice the model to fit the memory, and then you copy that sliced model to fill the entire data center.
It's like building a Voltron and then building an entire army of Voltrons.
That is actually a perfect analogy, yes.
Yeah.
You are combining the unique strengths of both methods.
So, zooming out a bit, why does this specific paper matter to the person listening right now? Because we aren't all training billion parameter models in our basements.
It matters because it was the green light for the whole industry. Before this paper, we knew we wanted bigger models, but we honestly didn't know if we could physically build them or if they would just break the hardware.
Megatron-LM proved that the memory wall is permeable.
It turned a physical impossibility into a solvable math problem. And more importantly, it democratized the technique.
Because they didn't lock it behind a proprietary compiler, right?
Right, it's built in standard PyTorch. It meant that any organization with the hardware could start training these absolute giants.
And we've seen the legacy of this everywhere. Microsoft used this exact framework later, didn't they?
They did. They used Megatron to train Turing NLG, which was 17 billion parameters.
Wow.
And since then, we've gone to 175 billion with GPT-3 and now into the trillions. But the fundamental technique, how you slice the attention heads, how you split the matrices, it all traces right back to this paper.
It's the blueprint.
It really is. It also taught us that hardware and software can't be designed in vacuums anymore. If you want to build a digital brain, you need to deeply understand the silicon it lives on. You need to know exactly how the wires connect.
The paper actually ends on a forward-looking note, suggesting that we will need even more complex hybrids of parallelism in the future as these things grow.
And they were totally right. Today, we use tensor parallelism, which is what Megatron introduced, combined with pipeline parallelism, combined with data parallelism. It's a three-dimensional puzzle now.
But the pieces were cut here.
Yes.
Well, we've covered the memory wall, the really elegant row column slicing, the pre-norm fix that saved BERT from collapsing, and the sheer scale of 512 GPUs working in perfect harmony. It is just a masterclass in systems engineering.
It's a great reminder that sometimes the biggest breakthroughs aren't brand new algorithms, but just much better logistics.
That's a perfect way to put it. Now, before we wrap up, I want to leave you with a thought. The authors of this paper unlock the future of AI by figuring out how to surgically slice the math across the chips. They proved that the bottleneck wasn't the intelligence of the design, but just how we held the knife. But here is the question for you to chew on. If the only thing stopping us from smarter AI was the logistics of memory, now that we've solved that, and the hardware is only getting bigger and faster, is there a limit left? Or have we just removed the last guardrail on the highway to superintelligence?
That is the big question.
Thanks for listening to this deep dive into Megatron-LM. We'll see you next time.